So what we saw above was that the refractive index, as we went to longer and longer wavelengths and lower frequencies, then the reflectivity increased for some of the metals that we spoke about in the last section. If we look again at equation 45, then if omega is very, very much bigger than omega naught and is also very much bigger than the damping term, I times the damping term, then we can simplify the equation for the refractive index into something which looks like this. Now, we've got an n squared and we've got a right hand side. And that right hand side, if this number 1 minus n times qe squared over epsilon naught me omega squared is a negative number, then the square root of that negative number means that the refractive index will be complex. If this number is a positive number, or 0, then the refractive index will be a real quantity. So if this value in the brackets is bigger than 1, then the whole expression will be negative, the refractive index will be complex, and if that expression in the brackets is less than 1, then we'll have a positive value for the refractive index. When we have a frequency which is very much bigger than the characteristic frequencies in the material, then we refer to that as the plasma frequency, essentially because we can think of the metal as being composed of the free electrons and positive ions. So the plasma frequency is related to this here. We're going to plasma frequency as being the square root of n qe squared over epsilon naught me. And so our refractive index then can be defined as being 1 minus omega p over omega, the plasma frequency divided by. Now, if the thing in the square in the curly brackets is bigger than 1, then n will be complex. And if the thing in the brackets is less than 1, then positive. It's a real number. So in other words, if omega p is bigger than omega, then what we're going to do, what we'll get is a complex refractive index, and at frequencies above omega p, in other words, when omega is bigger than omega p, then we'll have a real refractive index. Okay. So when the frequency is less than omega p, then this number in the bracket will be bigger than 1, and so we have a complex refractive index. And when omega is bigger than omega p, the thing in the brackets is less than 1, and we have a real refractive index. When we have complex refractive index, that means that the wave which penetrates into the metal will have an exponential decay from the boundary, and for omega p real, the absorption is small and the conductor then becomes transparent. So in other words, if we go above the plasma frequency, we can actually see straight through the metal. It becomes transparent instead of opaque, and the light can travel straight through it. If we look at some of the frequencies for different materials, then you can see that these are very simple elemental metals, so lithium, sodium, potassium, and rubidium. This is the measured wavelength, and then that's the calculated wavelength. And you can see that for very simple metallic structures, then we get a fairly good agreement. And you can see again that the oscillating frequencies 10 to the 15 to 10 to the 14 plasma frequency for the measured plasma frequency for these metals. So the theory is very crude, but it does give us reasonable approximations to what we see for very simple materials. When we go to more complicated materials, obviously, the situation becomes more complex, and we have more factors that we need to take into consideration.